Hello, everyone. Welcome to a new session of the TVS Colloquia series. So today we have the pleasure to have with us Dr. Brian Kloppenborg. I hope I
Yep, you
pronounced
got
this
it.
almost right. Okay. He's the executive director of the American Association of Variable Stars Observers. He did his PhD and then two postdocs working on variable stars. Then he left for a little bit, and now he's back as the executive director of this association. And now he will tell us about their work with amateur astronomers. So take it away.
Yeah, thank you. Yeah, thank you, Priscilla. I appreciate it. Yeah, it was interesting having a career trajectory where I started out in astronomy and then left for about a decade, and now I'm back, leading one of the oldest astronomy organizations in the world. So it goes to show you that even if you don't take a fairly traditional path, you can always come back to astronomy. So thank you again for allowing me to come and speak with you all today. I'd also like to thank a couple of other people along when I go through the presentation as well for just setting up this meeting and giving me an opportunity to talk with the transient and variable star group here. So today I'm going to present a talk that I actually retitled the talk yesterday after reading the white paper from the TVS team. And so today I'm going to be talking about AAVSO and the modern amateur astronomer. So in today's talk, I'm going to present just a few slides that discuss the AAVSO, and I've tailored the material mostly to the material that I think, based upon the white paper, that the TVS group might be interested in seeing. I'm going to talk about modern amateur astronomers and their capabilities, and I'll also present several science highlights. Unfortunately, I pulled a couple of things out from my abstract, so I won't be talking about some of the solar-based work as well as a couple other things there. But I think I still found a couple of great examples of recent science from the amateur astronomical community that will be of interest to this group. And then lastly, I'm going to talk just briefly about how I personally think it's best to get amateurs engaged in your research and how you might work with them to produce really awesome science. So first off, about the AAVSO. The AAVSO is a 112-year-old organization. Our mission is to enable anyone anywhere to participate in scientific discovery through variable star astronomy. And we achieve this mission through pro-am collaboration primarily, as well as strategic partnerships, educational activities, and data stewardship. And in the next couple of slides, I'll give some examples of each one of those different activities. So one of the most interesting things that I found about becoming the executive director at the AAVSO, which I just celebrated my first year anniversary here on the job, is just how diverse of an organization this actually is. So the things that kind of unify the members of the AAVSO and our observers is they all kind of come from a wide variety of different backgrounds. So they're usually high schoolers to retired career professionals. But the unifying characteristics is that they're all interested in astronomy in one way or another, and they also want to contribute to science. Now, where the organization really starts to diversify is that it comes to their different capabilities that they have. So about 20% of our members at any given time need some form of education. So they're trying to learn how to do variable star science. And so the AAVSO provides them with training and guidance and mentoring. About a good chunk of our members, approximately 70%, are out there working with professional astronomers in one way or another. The predominant thing that they do is collect data on behalf of professional astronomers and then upload that data to the AAVSO's database, which we curate. And then somewhere between 2%, which I know is a minimum threshold because I've actually counted these people, up to perhaps about 10%, are out there doing the full scientific method themselves. So they're defining a hypothesis, they're designing an experiment, they're out there collecting data, and then they're analyzing their data and they're publishing their work in various scientific journals. And so those people are kind of like, I would say, like high-end graduate students in terms of their capabilities. Now, to further diversify the organization, they also have a variety of different instruments. So the AAVSO, for a very long period of time, going clear back to its history, we accepted data that was taken by eye, so visual observations. But nowadays, people are also using DSLR sensors, so point and shoot cameras, basically, as well as CCD and CMOS detectors. In terms of optics, they have nothing up to kind of meter class telescopes. And then in terms of tools, basically they use everything that you guys can use. If it's an open source software package, I can probably find somebody that's actually using it. We have people that have high resolution spectrographs. I think I pulled that from this presentation, but there is one gentleman that has a R30,000 fiber fed spectrograph connected to a 1 meter plane wave telescope that he uses on a fairly regular basis. There's also folks with Speckle cameras and a variety of different software packages as well. On the right-hand side, you can see photos of a subset of our AVSO members at the 2022 annual meeting, which is the one that has it was down in Tucson, so it's the one that's a little bit more arid looking in the background. And then in the upper right-hand corner, that was at our last annual meeting up in Boston. Down near the bottom, I'd just like to call your attention to a couple of different people, which shows you a lot about how the AVSO works. So Roger here, he likes to observe visually using telescopes that he built himself. And so you can see him there with his telescope. Mario Mota, he likes to build machines himself. And so he's standing next to an 80 centimeter telescope that he actually constructed from scratch. He actually sold that telescope to Arnie Hendon, who was the twice previous executive director. And so I'm looking forward to getting to know Mario a little bit more during my career in hopes that I can get one of his next telescopes. And then in the bottom right-hand corner is Sansu. He's really interested in observing the sun. And so he went out and built his own handmade solar telescope. So it's interesting to see that we have people that are not only interested in just observing things, but also building things as well. Now, this is a slide that I like to present that really summarizes the AVSO in kind of just a broad swath. And so it just summarizes our organization in terms of numbers. So as I mentioned already, the AVSO started back in 1911 with the explicit purpose to observe variable stars and kindred objects. At present, we have about 1,200 members, 800 observers, and 200 volunteers. We have 7 staff and 2 contractors and operate on a $1 million per year budget. We conduct a variety of different education and public outreach activities, which include webinars that reach about 10,000 people annually. We have continuing education courses, which are these 10 choice courses that have about 125 participants every single year. We also have 7 different observing manuals that describe how to do variable star observations, either visually with your eye or with various types of detectors. Those have been translated into 13 different languages by some of our volunteers. And we also have a fairly extensive mentoring program. Now, one thing that I really like about AVSO is in the upper right-hand corner, which is our contribution to science. So our data or products or services are used in about 325 publications per year. And in terms of data, that includes our photometric database, which has 59 million observations. We have a curated variable star metadatabase called VSX, which I'll talk about here in a minute, that has about 2.2 million observations. Our solar database is one of the longest running records of sunspots and sunspot groups, has over 275,000 observations from about 71 different observers as of today. We recently started a spectroscopic database as well as an exoplanet transit database, and we also have a peer-reviewed journal. So despite the fact that we're an organization that focuses primarily on variable stars, we do have a lot of different data products. We also have some other activities, including our annual variable star meeting, which I just mentioned prior to the beginning of this talk, where Dr. Paula Scoti presented the Arlo Landahl lecture, as well as we produce proceedings for that meeting, as well as have a variety of different workshops throughout the year. So just to show you that the AVSO is a really serious scientific organization, this is the plot of the last 10 years worth of publications that use AAVSO or at least reference AAVSO within their document. I went through every single paper that was published in 2022 and categorized them, and I'm not going to show that here, but the vast majority of them were actually using data products or services, and only a very small fraction of them were actually just kind of mentioning the AVSO and kind of a passing reference. So in 2022, there were about 285 peer-reviewed, refereed publications, and 65 that were non-refereed. And as of the beginning of November this year, there were about 226 papers that were published in various scientific journals that were refereed. Of course, that number will continue to go up throughout the rest of the year. One of the primary things that people know about the AAVSO is our photometric database. That's the AAVSO International database. Here I show a couple of different examples of some data from there. I'll mention that it's the largest source of amateur photometry that's out there, with over 59 million observations and active monitoring of about 32,000 stars. Most of the data that we have within the database is visual, meaning by eye. However, starting kind of in the year 2000, we started to get a variety of different other sensors. So there's Johnson-Cousins and slowed filter data in there, as well as some narrowband observations. In the upper left-hand corner is one of my favorite plots. This is of a recurrent nova called SS Cygni. You can see there that the data goes clear back to 1890 in the upper left-hand corner, and every single one of these spikes is an eruption. And I believe we haven't missed a single eruption since kind of like 1907. And you can see here around the year 2000, all the black data here is visual data, so it's all by eye. And then around the year 2000, when CCD detectors started to come out, you can see that the green data, which is CCD data, starts to kind of come in. I've also used a lot of data from the AVSO as part of my dissertation work on Epsilon Arichi. Here you can see photometry of the 2009 through 2011 eclipse, and I'll talk about this in a few slides. That shows UBVRIJH photometry, all taken by amateur astronomers. And then over here on the right-hand side is some work that we did on Nova Del, which actually got published in Nature as well. You know, a wide variety of different objects that we're looking at here. One of the databases that I'd like to point out that I think is probably of high interest to the TVS team is the Variable Star Index, or VSX. This is kind of like basically ADS for variable stars. So we have captured about 2.2 million stars that are all of the known variables that have a variability of 1 millimagnitude or more. And this database allows you to search and query by name, by coordinates, by minimum, maximum magnitude, spectral type, variability type, etc. And we also have links that point out to a variety of different sources of data that exist out there. We've been working with the Gaia team for the last several years to ensure that VSX is as accurate as possible. And Gaia has actually been using VSX as their primary reference for variable star data. As the Vera Rubin Observatory comes online over the next couple of years and you start doing a lot of data science and data mining activities, we'd encourage you to come back to VSX and, you know, kind of check our entries and just, you know, one, make sure that our entries are actually appropriately coded, but I'd also encourage you to use it for various data science activities as well. If you'd like to know more about VSX, you can check it out at aavso.org/VSX. We also have a spectroscopic database, which I alluded to just a little bit ago. This is a fairly new program, which we started back in 2017. And you can see some examples of the type of spectra that we collect there on the right-hand side. There's one spectrum of beta Per in the upper right, which is taken with an instrument called a Star Analyzer 200. It's just a diffraction grating without any kind of slit in front of it. But then observer KMWA down in the lower right-hand corner for his observation of NSV 1972, he's actually gone in and optimized the optic train so that he gets even better resolution out of this fairly simple device. Another great example is down in the middle here, observer GOLA. They have a very beautiful spectrum of the P Cygni profile in P Cygni. So lots of different spectra here that might be of interest to you as you're conducting your research. AVSpec is not the only spectroscopic database that's out there in terms of amateur spectroscopy. We're actually one of the smallest right now, but we're growing at the most rapid pace. So AVSpec just focuses only on variable stars, and we have about 12,000 entries. There's the RS database, which has symbiotic nova and dwarf nova observations, and they have about 13,000 stars. The British Astronomical Association, they started a spectral database a little bit before we did, and they have about 13,000 spectra, but they basically allow anything within their database in terms of astronomical sources. And then one of the longest running spectroscopic databases is BESS, which focuses on BE and Herbig stars. So these are some other places that you might be able to go to get some data. The AVSO also started an effort to observe exoplanet transits back in 2018. We partnered with NASA's Exoplanet Watch. Here's some examples of the different types of data that you can see. Within the AVSO's database, you get like a trace that's in the upper right-hand corner where you can see a fairly clear 12 millimagnitude drop when this particular exoplanet was transiting its host star. And then using the Exoplanet Watch software, you can actually average the data and fit it to some kind of a model curve. And so it's been a really good partnership for us. Now, I will mention that, we're relatively small in terms of the exoplanet game. The NASA Exoplanet Archive is much larger than what we are. as well as the Czech Astronomical Society has a database called TRECA, where they have about 11,000 transits compared to our 4,600 transits. So we're slowly catching up, I think, in terms of the exoplanet game. One other thing that may be of interest to the TVS group here is the AVSO's photometric all-sky survey called APASS. This project ran from 2010 through 2018, and it basically bridged the gap between Tycho and SDSS and filling the gap from 7 to 17th magnitude. It caught Johnson's B and V as well as Sloan filters, which you all are using within LSST. And so I think it's probably a good database that you could check out. Right now, DR10, data release 10 is on the AVSO's website only, but DR11 is out on Vizier and the virtual observatory. Now, the AVSO, it sounds like we're just focused on variable stars, and we've taken the liberty to interpret variable stars and kindred objects as broadly as we possibly can. Here's some examples of how researchers used AAVSO's data within 2022. When I skimmed all of those 300 and some odd publications from 2022. As you can see here, about 2.1% of our observations are focused on Mira stars, 3.5% are on supernova. Cataclysmic variables amounts just about 4%, and blazars about 1.3%. In the upper right-hand corner, 4.6% of our citations are focused on exoplanets. Young stellar objects make about 4%. Kind of our bread and butter, though, is really down in binary stars, which is about 14% of the papers we're referencing, and the nova, of course, are incredibly popular with everybody, and so there's about 14%. So despite the fact that we talk just about variable stars, there's a pretty good diverse set of things that we actually go out and observe and collect data on. So now I'd like to transition away from talking about the AVSO to talking about the modern amateur astronomer. One of the most amazing things that I think occurred during the decade when I was out of astronomy is just almost the proliferation of low-cost sensors and a variety of different other technologies that allowed amateur astronomers to basically close the gap between the things that they're doing as amateurs and the things that we're doing as professional astronomers. So my first slide here is just that amateur astronomers are extremely capable nowadays. So I've pulled out a few things from the Society for Astronomical Sciences 2023 proceedings on the left-hand side, as well as the Journal of the AVSO and the BAV magazine Spectroscopy that shows these are common publications that amateurs like to work in. So in the upper left-hand side, there's a group of amateur astronomers that are designing a R30,000 spectrograph from scratch. That's called the Flex Spec 1. I've actually held one of these units in my hands, and it actually works really quite well. There's folks doing Speckle interferometry as well as exoplanet transit photometry, and then follow up to the DART mission and the monitoring of ammonia on Jupiter's atmosphere, as well as optical SETI. In the 2022 proceedings, there were also people that were doing binary star modeling using Phoebe, and they were not only just looking at detached binary stars, but also close by symbiotic stars. And so there's a lot of really cool research that's coming out of the amateurs community. In the upper right-hand corner, the Journal of the AAVSO. This is a peer-reviewed journal. In our latest issue, we had some folks that were looking at the period luminosity and metallicity relationship and modeling that to try to pull things apart a little bit when it comes to regular like fundamental mode pulsating stars. A lot of work on eclipsing binaries as well as flare star monitoring. And probably one of the most impressive projects that I've seen in the last couple of years in the BAV magazine Spectroscopy, there was a gentleman that built a homemade spectropolarimeter, and it was completely 3D printed, and with the optical elements they purchased online. And having worked with a couple of people that do spectropolarimetry, I have to say that an amateur doing that is just frankly insane. It's amazing to be able to see people doing that. So kind of the key takeaway here is that the research from today's amateur astronomers, at least in my opinion, is kind of comparable to that of professionals from 1990 through 2010. And it's really been enabled through the proliferation of low-cost hardware and open source software, as well as other things like that really facilitate the research. So I'd like to talk just briefly about the photometric capabilities of amateur astronomers, and I've presented this slide here kind of in a tabular form to help you get an idea of how these folks might work with you with the Rubin Observatory's various projects. I've listed it here by instrument, including visual, which again means by eye, CCD CMOS sensors, as well as photoelectric photometers. To a lot of people, it's surprising to hear that photoelectric devices are still being used, but they're actually one of the best objects to monitor bright stars. So in terms of these different sensors, you can see in the third column from the left-hand side that with visual, folks are going all the way from the brightest stars that you can see by eye, just by standing outside, out to about 16th magnitude if they're using various telescopes to look at things. The CCD and CMOS observers are out looking with Johnson-Cousins filters as well as Sloan filters, covering everything from about 2nd magnitude down to 19th magnitude. And photoelectric photometers still really popular, mostly observing in visual bands from view out to eye. But then there's also a very small number of people that have Optec brand JH photometers, and they're mostly limited from -4 to 4th magnitude. The really cool thing about the photoelectric photometry people is their data tends to be the most precise because they have very tightly controlled standards in terms of the stars that they use as calibrators, as well as they all have basically the exact same instruments with the exact same filters and the same data reduction techniques. And so they produce a really tight kind of like 5 to 10 millimagnitude error on most of their observations. So now if we compare the capabilities of amateur astronomers with various sky surveys that exist out there, we get a plot like what you can see here on the left-hand side. And just to kind of take you through it, on the vertical axis is its magnitude range, and on the right-hand, the horizontal axis are different photometric sky surveys. I plotted out LSST on the Vera Rubin Observatory here on the far right-hand corner. The color that you see in the background denotes the number of filters that are being used, with the red to blue kind of as 2 filters. The red to green to blue is 3 to 6 filters, and the red to yellow to green to blue is 6+ filters. And so you can see here that amateur astronomers really span a fairly large range of different magnitudes, all the way from about -4 to about 19th magnitude. And at the fainter end here, it overlaps with a large majority of the different sky surveys that are out there, including the upper end of the limitations of LSST on the Vera Rubin Observatory. And so I think, just kind of making some broad strokes here, that amateur photometry is really quite complementary to most of the modern sky surveys. And in particular, those sky surveys that only use one filter, which are all of these open bars that you see here. Amateurs can really produce a lot of data that can be complementary just by kind of filling in the gaps. Now, to do a couple science highlights, I'd like to first kind of give a shout out to a former colleague of mine, Jeff Hopkins and Robert Stencil. So Jeff Hopkins, pictured here on the left-hand side, he observed the star called Epsilon Arichi for over 27 years. And he and Bob met back in the 1980s. You can see both of them here in the middle. Bob Stencil on the right-hand side, Jeff Hopkins there on the left-hand side of that box. Bob convinced Jeff that Epsilon Arichi was probably the most interesting star in the universe, and it was a 200-year mystery. And so I'd like to say that it actually was pretty interesting in the end. And so leading up to this eclipse that occurred in 2009 through 2011, Jeff basically marshaled the amateur astronomer community to go out and start doing observations, while Bob Stencil managed the professional astronomical community. And they really hit the system quite hard. And this is really kind of where I got involved. But you can see here Jeff's data going in the lower left-hand corner, going from back in the 1980s all the way up into the 1990s. It's in Julian dates, but I'll let you know that in the end here, it's about 2009 is the lower right-hand corner here. You can see that he just clicked to the star every couple of nights, and it's doing a lot of really interesting things. Sometimes it's flat, sometimes it's wiggly. There's actually one instance of a flare that he caught kind of back in 1986 or something like that. So really interesting to see a person just sit there and monitor a star for many, many decades like this. You're almost never going to get that out of the professional community. And even with LSST having, say, like a 10-year lifespan, which I really hope becomes something more like 20 years, you're still kind of about 7 years short of what amateur astronomers will do if you get them on your side. Then in the bottom middle here, I've already shown you this plot once, but this is again UBVRI-JH photometry from the AAVSO Citizen Sky project that was taken during the eclipse that occurred in 2009 through 2011. You can see here in black, which is the H-band data, that it's a really anomalous, kind of fairly long event. So when I got involved here, I started interacting with the amateur community basically from the get-go because Bob Stenzel was a very strong proponent of amateurs getting involved in astronomy. My dissertation work was focused on doing interferometric imaging of the system, but then I combined optical interferometry with radio velocity data with the photometric data to actually model the system as it was in eclipse and produce some really interesting results here. And this system, it's a binary where one of the stars is not actually observable because it's encased in a disk of opaque material. It's seen almost entirely edge on, so we can only see one of the two components, so single line spectroscopic binary situation. And you can see here in these images in the upper right-hand corner, there's like about half the star disappears during the eclipse, which explains why the system gets so faint. And this observed silhouette here in the bottom half, this is basically holding the disk of opaque material fixed and then allowing one of the stars to slide behind it. Now, I wouldn't have been able to do most of this modeling if it weren't for the amateur photometric data, particularly the data that was taken out in the H-band. And so I'm really quite grateful for them spending time and working on this effort. Popping over from binary stars, well, I guess I'm still in the binary star category, but over to eclipsing cataclysmic variables. This star here, V808 Arichi, is presently being monitored by David Young. This is a star that was discovered as being variable in 2009 in the Catalina Sky Survey and was later classified to be an eclipsing cataclysmic variable. And you can see here on the right-hand side, this is David's photometry that he's collecting with his personal 1-meter plane wave telescope. The error bars are probably just a little bit bigger than what these boxes are. Some just absolutely stunning photometry that you can get out of the amateur community. And his data has actually been used to help interpret the system in a variety of different ways. In addition to doing photometry of the system, he also has a fiber-fed a spectrograph that he occasionally uses to collect R30,000 shell spectra of the system. You can find these kind of power users out there in terms of amateur astronomers that can do some really exceptional work. You probably all heard about Betelgeuse dimming a couple of years ago. I'd just like to say that it was an amateur astronomer who was the person that was out there monitoring the system, and they rang the bell. So AAVSO member Tom Calderwood, he was monitoring the system basically for the last 15 years, and he noticed starting in late 2019, the system started fading somewhat anomalously, and he got the attention of Edward Guinan, who helped him publish the astronomical telegram that you see in the upper left-hand side. And Tom has continued to monitor the system since, all the way through the Great Dimming. In exchange for him going out there and collecting this really excellent photometry, the error bars here are probably just a little bit bigger than the points. This is photoelectric photometry, mind you. He got his name on this publication that you see on the left-hand side in the Astrophysical Journal, and then his data was also used to do some interpretation of this, what ended up being a dusty ejection, kind of like the star was basically belching out a bunch of material out into space. His data was actually used in this Nature publication that's featured on the right-hand side here. So, incredibly great work, I think, being done by Tom. Now, switching away from photometry and popping over to spectroscopy for a little bit, this has been one of the most interesting developments, I think, within amateur astronomy in the last decade, is the wide variety of different instruments that are available to them at fairly affordable costs. So you've already heard me talk about the Star Analyzer 200, which is a wide field slitless device. It's just basically a diffraction grating that sits in a filter holder. The magnitude limit for this type of a device is about 14th magnitude, and it produces spectra that are kind of around 200 resolving power in terms of its maximum resolution. And that goes all the way up to different devices like the LP600, the LISA low spec, the eShell, the L high-res 3, and the Shellyak whoop shell, which is this R30,000 device that's fiber fed. A lot of amateur astronomers now are exploring spectroscopy, and they're very interested in helping out professional astronomers in any way that they can. I would say probably most of the devices that you're going to see are kind of like either these low resolution diffraction gratings. That's very common basically worldwide. And then there's a few people that have things kind of up to R of 10,000. But then I think in terms of these R30,000 devices, there's really fewer than 10 of them exist. I know where 2 of them are, but not where the other devices are. But it's really interesting to see that amateur astronomers now have access to basically professional grade instruments that allow them to do cool science. Just like I showed previously, I'd like to talk about how amateur spectroscopy devices compare to that of different sky surveys. So in the upper right-hand corner, um, I plotted out the wavelength coverage here versus different types of amateur devices going from the low resolution all up to high resolution devices, and then different sky surveys plotted out here on the right-hand side. You can see basically in terms of wavelength coverage, there's a pretty good overlap between amateur astronomy equipment and most professional grade stuff, except for a few that go out kind of into the near infrared bands. Unfortunately, in terms of like the limiting magnitude, most of these devices, coupled with their telescopes that they operate on, usually can't get fainter than about 14th magnitude. So it seems like it's probably unlikely that most amateur astronomers would be able to contribute to the objects that LSST will be looking at. But there are a few out there, as I mentioned a while ago, that do have 1 meter telescopes and high resolution spectrometers. And so if you're interested in getting follow-up spectra on some of these devices, I think it would be a good opportunity just to kind of reach out and see if we can find somebody that could, partner with your research. One of the more interesting projects that I've seen being done by amateur astronomers recently is this red dwarf flare star project. And this is to quote Bob Buckheim down in the lower right-hand corner, it's a good demonstration that amateur astronomers are they're happy to squander their resources in the name of science. This consortium here, they point at a small number of stars and they just park their telescopes on them. This is incredibly risky science that no professional astronomer would be able to do simply because it's just too time consuming in terms of resources. So they're out there monitoring these stars both photometrically with observations that are kind of on the order of somewhere between 10 to 30 seconds, depending on the different stars that they're looking at. And they're not only observing them photometrically, but they're also observing them spectroscopically. And as shown in the lower right-hand corner, this star here, EV-LAC, they caught two different flares that occurred back earlier this year. And in addition to monitoring them photometrically, they also looked at them spectroscopically and measured the equivalent widths versus time of various lines. And it was really interesting just to see the amount of energy that's dissipated and how how the response of the star's atmosphere as well as its circumstellar environment are reacting to the presence of flares. So probably one of the more interesting projects I've seen coming from the amateur astronomical community in the last few years. Outside of photometry and spectra, I'd just like to point out a couple of other things that amateur astronomers are doing. Speckle interferometry is definitely within the reach of most amateur astronomers now. David Rowe in particular has developed some software which makes it really easy for them to interpret the resulting speckle patterns into, to do the image deconvolution there. Russ Genet is probably the best known person that's out there promoting speckle interferometry. He has a activity where he brings in students up to Mount Wilson every single year and has them use the 60-inch telescope along with a speckle camera and then has them publish papers. And one example of that is on the right-hand side here of some automated speckle work that they were doing on some different known binaries. They're fairly typically, they can get down to 200 milliarc seconds or 0.2 arc seconds in terms of resolution. So it's definitely something that's doable by most amateurs nowadays. And just to kind of complete the loop here, I'd like to talk about something that's outside of the normal stellar environment as well. There's a very large group of amateur astronomers that are interested in asteroids and minor planets and comets just moving through our solar system. Bob Stevens here, he's the treasurer on the AAVSO board, and he's also one of amateur astronomers' most avid asteroid observers. Here's a couple of papers that involve some of his work. So on the lower left-hand corner, some of his photometry on this particular asteroid, 2346 Lilo. And you can see here that they were able to do shape modeling in the lower right-hand, in the bottom middle portion of the screen here. And then recently, there was a really cool paper that was published that looked at a whole bunch of Jupiter Trojan asteroids. They did 53 different asteroids that they modeled, and almost 70% of that data came from Bob Stevens. So it really goes to show you that amateur astronomers are interested in looking at different things. And if you know who to ask, you can actually find a pretty good data set of these. Now, AVSO is not an organization that goes out there and observes asteroids. That's mostly the International Occultation and Timing Association, or IOTA. And then NASA also has a group that go out and look at various asteroid transits as well. And finally, I'd like to wrap up just with a couple comments about how to get amateurs involved in your research. Having worked with the amateur community for about 5 years during my PhD, and then coming back to it now as the executive director of the AVSO, this is kind of my advice here. So if you're going to get involved, if you really want to get amateurs involved, the most important thing here is that you communicate to them relatively clearly. Specify what the goals of the project are and what their objectives are. Tell them how their data is going to be used, and tell them about your timeline up front. A lot of amateur astronomers get quite frustrated when they give data to you and then it kind of disappears into a black hole and it doesn't get published for 4 or 5 years. Some of them are very highly motivated and they want to see their names on publications. Other ones just want to know that you're going to do good things with the data. And so it's best to be fairly explicit about your particular goals, expectations, and timelines up front. The next thing is pick projects that are fairly reasonable. Now, despite the fact that there are a couple people out there with half-meter telescopes up to 1-meter telescopes, most people, at least in the United States, have 40-centimeter telescopes with fairly modest equipment that's attached to them. In terms of their observing capabilities and their expertise, most of them have some form of an advanced degree. So at least within the AVSO, we have a lot of doctors and lawyers and other career professionals, but few of them have a formal education in astronomy. So when you talk with them and describe your project, you'll find that you often have to explain to them things that if you were talking with a graduate student, you wouldn't have to explain to them. But they catch on really quick because they are very smart people, just not very experienced with astronomy in terms of having a formal education. And then in terms of their time commitment, a lot of people think that amateur astronomers are basically like an unlimited source of resources, which, for some people, they have robotic telescope farms with 6 to 8 telescopes, and they're out there observing basically everything they can possibly observe. But those are our power users. Most people will invest maybe about 1 to 2 hours per day, and very few of them have completely automated systems. One of my best friends, who's an amateur astronomer, he goes out there and he enjoys observing visually just with his eyes, but then occasionally he'll bring out his CCD and he'll put a V filter in there, but he has to manually change his V filter because his resources are quite limited. In terms of training and support, keep in mind that you can have a fairly wide variety of people that are engaged in your program. Some of them might just be starting out, and so they're going to need a lot of handholding, a lot of instruction, and some ideas of just basically how to get going. And then you'll have a small number of people that are very advanced in terms of their observing capabilities. Now, it's somewhat difficult to deal with such a diverse group in terms of experience. And so I'd really suggest that you partner with some citizen science group like the AAVSO or Exoplanet Watch or IOTA, as well as SETI and Unistellar are also doing really interesting work with amateur astronomers right now. One of the things that I think is probably essential is that you need to interact with them. A lot of professional astronomers, we're kind of spoiled nowadays where we have the ability to go out and collect data just from a variety of different sky surveys, but you have to keep in mind that the amateurs that are out there getting data for you are people. And so you need to talk with them kind of at least once a week and try to build long-term relationships. And I think the example of Jeff Hopkins and Bob Stenzel is a great showing where you had one amateur astronomer that basically spent a significant fraction of his life observing one star for a professional astronomer, and they were basically best of friends in the long run. And so building those types of long-term relationships is actually quite fulfilling and also very useful for your career. And then when it comes to acknowledging them, treat them as if they were your peers. Certainly put them in the acknowledgement section at a bare minimum, but in many cases, apply the standard prudence that you do for co-authorship and consider listing them as a co-author, especially if they contribute significantly to your paper. And now here on my last slide, I'd like to talk about some different collaboration opportunities that we have. So the AVSO's focus area is primarily going to be maintaining and building our knowledge of bright stars. So basically stuff that's brighter than 15th to 17th magnitude. We're going to be spending our time to educate and prepare amateur astronomers for contributing to science, as well as producing high quality data products. And so that's where the bulk of our organization is going to focus our efforts. But for the transient and variable star group here, I spent a lot of time talking with Rachel Street about the alert broker system. And one thing here to note is that I think the system is really quite well designed, and it's a good idea to get those alerts out there. But in order to entice amateur astronomers to go out and observe your targets, they're going to need to know why things are interesting and why they should be investing their limited resources and limited time to observe those objects. And if you have a particular type of star, I will say that like supernova, everybody gets excited about them. Nova, everybody gets excited about them. But binary stars and young stellar objects and sometimes cataclysmic variables, it takes a little bit of convincing to get people to go out and observe those things. And if you need some language or you need a little bit of help getting amateurs excited about those things, feel free to reach out to the AVSO, and we'd be happy to lend you some words that you can use to talk with them. I think that looking at the bright transients, there's an opportunity for either AVSO collecting spectra on some of those things. There's, again, very few people that'll be able to reach the limited magnitude, the upper magnitude range, I would say, of LSST. However, there are a few of them out there, and so for incredibly high value targets, we could consider collecting spectra for you. And then for those stars that are getting relatively bright, I saw in the white paper that you talked a little bit about doing handoff for monitoring those systems. So if it looks like there's something that's kind of going to be popping up to the upper limiting magnitude range of LSST, perhaps consider sending an alert over to the AVSO, and we can monitor that system and catch the peak and then watch it fade off again. And in terms of objects, I think that there's probably a really good chance that our members would be interested in observing supernova as well as novae or cataclysmic variables, as well as the brighter young stellar objects, blazars, and luminous blue variables. And so with that, I'd just like to say thank you for inviting me, and I'll open the floor to questions.
Thank you, Ryan, so much for this amazing talk. It's great to see all the nice and exciting work that you are doing at the AAVSO. And I look forward to seeing what amazing thing you do next.